Hi, everyone. Welcome back to the Readiness Review series for general chemistry. Now we're going to be talking about Lewis dot structures. So these structures are a way of representing atoms or molecules based on their valence electrons. And so what we do is we just represent the valence electrons of each atom, which are dictated by the column that they are in the periodic table. So we only care about the valence electrons because those are the electrons in the most outer shell, and those are the electrons that are used in bonding. So in order to build a Lewis dot structure, you first determine the total number of electrons there for the valence electrons. Then you just draw a skeletal structure of the molecular ion of interest, and then you choose a central atom based on the element behavior, and you add the surrounding atoms that are part of your structure. And once you create the bonds that you would expect, you add in the remaining electrons to the central atom. And then you rearrange the electrons in the outer atoms to best fulfill the octet rule if possible. So that was a lot, but we will go through some examples. So here we have some visual representations of the rules you just looked at. So hydrogen is in that first column. It has one valence electron, and bromine is in the seventh column. It's a halogen, and so it has 7 valence electrons. So when these guys bond together, the goal is to get bromine to have an octet, as hydrogen only has 1 valence electron and 1 electron in general. So it can actually only have a single bond, which was listed in that chart on the previous slide. So when they bond, they form hydrobromic acid, or HBr. And so hydrogen is satisfied because it has now at least an electron pair, as electrons prefer to exist as pairs. And now the bromine in HBr also has its octet rule filled. Same for H2S. So we have 2 hydrogens this time, and it makes sense that sulfur would be bonding to 2 because sulfur has only 6 valence electrons. So it needs 2 more electrons to reach those 8 electrons according to the octet rule. And so those 2 hydrogens go ahead and bond with those single electrons. And now sulfur is satisfied as it has 8 electrons, and the hydrogens are as well, as they now have an electron pair. Now, for nitrogen is one of the tricky elements that, like oxygen and carbon, can have double and triple bonds. And so nitrogen is in the 5th column of the periodic table. And so it has 5 valence electrons. So in order to get to 8 valence electrons, it needs 3 more electrons. It can bond with itself in order to complete the octet rule, and it does so through a triple bond. So instead of sharing a double, how in one bond, if it's a single bond, they share 2 electrons, double bond, they share 4 electrons, and triple bonds, they share a total of 6 electrons, each atom getting an extra 3. So each nitrogen in this case has now 8 electrons. So in this structure, we can have multiple options of where to put the double bond. As you can see, we have 2 single bonded oxygen to our central nitrogen and 1 double bonded oxygen. However, since it's 3 oxygens, we never actually know where the double bond is. But it doesn't matter because all of these representations are technically the same. So we know that nitrogen has 5 valence electrons and oxygen has 6 valence electrons. So looking at this first guy on the left, we know that nitrogen has 1, 2, 3, 4 bonds on it. And since it has only 4 out of the 5, it means it's missing an electron. So it's missing one of its normally negative charges. So that's why it has this positive charge here, indicating that it's missing that last 5th valence electron. And now as for the oxygen, this oxygen on top in the double bond has 2 electrons within the double bond, and then its normal 6 electrons. And then on the left and right sides, we have 1, 2, 3, 4, 5, 6. And then that 7th electron is here. So it has an extra 7th electron, meaning it has a net negative charge. Same goes for this guy. That 7th electron participating in the bond adds to the negative charge. And this can be distributed throughout. Doesn't matter where you put the oxygen, where you put the double bond, because it's same throughout.